Hello everyone, today I am going to discuss about compressible flows that includes introduction, thermodynamic relations of perfect gas or ideal gas, internal energy and enthalpy, speed of sound, pressure field due to moving source, basic equations for one-dimensional flow, stagnation and sonic properties, normal and oblique shocks. This forms chapter 1 of 5th module. Now, what is compressible flow and incompressible flow? We already discussed about compressible flow and incompressible flow in types of flow in second module. Now, let us just recall the concept. What is compressible flow and incompressible flow? Compressible flow is defined as that flow in which density of the fluid does not remain constant during the flow. That means density is going to change from point to point. But in case of incompressible flow, density of the fluid is assumed to be constant, that is rho equal to constant. For example, you can take into consideration of water that is assumed to be incompressible fluid which has a density of 1000 kg per meter cube irrespective of the temperature. Now, but in case of fluids such as flow of gases through orifices and nozzles are the devices used for measuring the flow. We are going to discuss about nozzles and orifices in third module. So next, in case of flow of gases in machines such as compressors and projectiles and airplanes flying at high altitude with high velocities, the density of the fluid changes during the flow. The reason for change in density is due to change in pressure and velocity. Let us discuss about basic thermodynamic relations. There are 4 basic thermodynamic relations. We already discussed about these things in basic thermodynamics. Let us just recall the concept. First one is characteristic equation of state. Second one is specific heat. Third one is internal energy. And fourth one is enthalpy. Now, what is characteristic equation of state? The state is defined. First we have to know what is state. State is defined as specific point which has specific properties, namely pressure, volume and density. So now let us go for characteristic equation of state. The characteristic equation of state for perfect gas or ideal gas that correlates the density of gas or volume of gas, absolute pressure and temperature is given by PV equal to MRT. Where P equal to absolute pressure in Newton per meter square or Pascal, V equal to volume of gas in meter cube, M equal to mass of gas in kg, R equal to gas constant in joule per kg Kelvin, and T equal to absolute temperature in Kelvin. Now we can simplify this equation 1 as P equal to M by V equal to RT, and M by V is taken as density, that is rho. Upon simplification we are going to get P equal to rho RT. Now, what is specific volume? Let us define the specific volume. Definition of specific volume. Specific volume is defined as reciprocal of density, or it is given by V equal to 1 by rho. So, unit of density is kg per meter cube. So, unit of specific volume is, it is exactly reciprocal, that is meter cube per kg. Substituting this value of rho in equation 1, we are going to get P by rho equal to RT, where R is gas constant. Now, let us define specific heat. What is specific heat? Specific heat for a solid or liquid is defined as amount of heat required to rise temperature of unit mass of substance to 1 degree or 1 Kelvin. So, unit of specific heat is joule per kg Kelvin. From unit itself, we can define the specific heat. That is, joule is unit of heat, kg is unit of mass, and Kelvin is unit of temperature. So, specific heat is defined as amount of heat required to rise temperature of 1 kg of substance by 1 kg by 1 degree centigrade. Now we have 2 types of specific heat. First one is specific heat at constant volume, that is Cv, and second one is specific heat at constant pressure, that is Cp. The relationship between Cp and Cv is given by Cp minus Cv equal to R and Cp by Cv equal to gamma. These are the very important equations that will be useful for solving the problem in fluid mechanics as well as ATD. So the value of Cp for air, it is taken as 1.005 kilojoule per kg Kelvin, and Cv, that is taken as 0.718 or 0.72 kilojoule per kg Kelvin. So upon dividing Cp by Cv, we are going to get gamma value as 1.4, where gamma is ratio of specific heat. Now let us define internal energy. What is internal energy? It is represented by symbol U. It is defined as amount of heat energy stored in a gas. The internal energy is due to because of kinetic energy and potential energy of molecule, electron or atoms that is contained in the system. So for perfect gas, internal energy is a function of temperature only, that is U equal to function of T. Now what is enthalpy? Enthalpy, that is represented by capital letter H or small letter h. So it is defined as amount of heat content used or released in the system at constant pressure. It is expressed as sum of internal energy and product of pressure and volume. There is an alternate definition for enthalpy. You can define enthalpy from expression H equal to U plus PV as it is a summation of internal energy and product of pressure and volume. So unit of enthalpy is joule for the capital letter H, and small letter h it is joule per kg. Now basic thermodynamic relations. There are about 5 thermodynamic equations. Let us discuss one by one. First one is constant volume process or isochoric process or volume equal to constant. Second one is constant pressure process or isobaric process or P equal to constant. Third one is constant temperature process or isothermal process or T equal to constant or PV equal to constant. Fourth one is adiabatic process, and fifth one is polytropic process. Now constant volume process, as the name itself indicates, here volume remains constant whereas other properties are going to change. So you can define a constant volume process as this. In this process system changes its state at constant volume. For example, heating or cooling of gas in an enclosed space or closed cylinder. So for state 1 and 2, expressions are given as P1V1 equal to RT1, P2V2 equal to RT2, where R is gas constant, T1 and T2 are temperature at state 1 and state 2, P1 and P2 is pressure at state 1 and state 2, V1 and V2 volume at state 1 and state 2. So dividing equation 1 divided by 2, P1 V1 divided by P2 V2 equal to T1 by T2. So, but here V1 equal to V2. So V1 V2 you can cancel here. So upon simplification we are going to get P1 V1 equal to P2 V2. In this system work done W equal to 0. Can you guess the reason? This is just because work done is given by integration from 1 to 2 PdV. As volume remains constant, dV equal to 0. So work done is equal to 0. Heat added, that is equal to, that is represented by Q equal to mCV T2 minus T1, where CV is specific heat at constant volume, T2 and T1 temperatures at state 2, 1, 1, and m is the mass of substance. Now constant pressure process, P equal to constant or isobaric process. This is similar to constant volume process. Here pressure remains constant whereas other properties, namely volume, density, that is going to change. So in this process system changes its state at constant pressure. For example, heating of a gas in a cylinder and piston moves against dead weight and keeps the pressure constant. You can take gas inside one piston cylinder arrangement. Upon heating, the gas expands and volume changes, maintaining pressure as constant. Now we have equation of state as P1 V1 divided by T1 equal to P2 V2 divided by T2. But here P1 equal to P2 because pressure is constant. So simplification, upon simplification we are going to get V1 divided by T1 equal to V2 divided by T2. In this system work done W equal to P into V2 minus V1. So and heat added equal to Q equal to mCp T2 minus T1. Now what is the difference between heat added at constant volume and heat added at constant pressure? For heat added at constant volume you have to consider specific heat at constant volume, and for heat added at constant pressure you have to consider specific heat at constant pressure, that is Cp. Now isothermal process, that is T equal to constant or PV equal to constant or temperature T equal to constant. Now what is the isothermal process? The process is called as isothermal when the expansion or compression takes place at constant pressure. So example, during isothermal expansion heat must be added continuously to keep the temperature constant, and during isothermal compression heat must be removed continuously. For isothermal compression the temperature for isothermal compression heat must be removed continuously to maintain temperature, that is T equal to constant. And in this process the gas obeys the law, that is Boyle's law, that is given by PV equal to constant or P is directly proportional to 1 by V, or you can write it as P is inversely proportional to 1 by V. or P is inversely proportional to V, or P equal to 1 by V. So upon this, using that expression, you can write expression for state 1 and state 2 as P1 V1 equal to P2 V2. So upon rearrangement, we are going to get V2 by V1 equal to P1 by P2. Also, P by rho, from equation of state we have P by rho equal to constant, because rho equal to 1 by V, that is specific volume. So heat added for isothermal process Q equal to P1 V1 ln of V2 by V1, that is equal to P1 V1 ln of P1 by P2, just because you can replace V2 by V1 by P1 by P2 because of the expression you have obtained, that is as shown above, V2 by V1 equal to P1 by P2. So you can replace, in place of V2 by V1, you can replace V2 by V1 by P1 by P2. Next, adiabatic process. An adiabatic process is a process in which there is no heat transfer from the system and vice versa. That is, from the system to surrounding or from surrounding to system, there is no heat transfer. So heat added Q equal to 0. Now work done for adiabatic process is given by P1 V1 minus P2 V2 divided by gamma minus 1 equal to R into T1 minus T2 divided by gamma minus 1. This is just because P1 V1 equal to RT1 from equation of state, P2 V2 equal to RT2 for 1 kg of mass. So where gamma is specific ratio of specific heat, that is for air it is taken as 1.4. In this process, PV to the power gamma equal to constant. For state 1 and 2, you can write expression as P1 V1 to the power gamma equal to P2 V to the power gamma equal to constant. So from equation of state, we have expression P by rho to the power gamma equal to constant, because V equal to 1 by rho. If the pressure and density are related in such a way that gamma is not equal to Cp by Cv, that is not equal to 1.4, but it is equal to any positive value other than 1.4, then the process is called as polytropic process. For example, Pv to the power 1.3 equal to constant. This 1.3 is not equal to 1.4, so this process is called as polytropic process with polytropic index 1.3. So P by rho to the power n equal to constant, or you can write Pv to the power n equal to constant where n is not equal to gamma. This is all about the basic thermodynamic equations. In upcoming videos, I am going to explain about derivation for velocity of sound. Thank you.